So last time I had mentioned that we are going to learn how to solve Rubik's Cube using GAP. So GAP stands for Groups, Algorithms and Programming. It's a software and it's a free software. You can use it in various operating systems, Windows, Linux, Mac, and this software was maintained earlier at place in Germany, Aachen, and currently there are 4 places all across the world where this software is, this project is being coordinated through. So Aachen, Braunschweig in Germany, St. Andrews in Scotland and Fort Collins in United States. So these 4 places are maintaining this software. So what is the specialty of GAP? Specialty of GAP is that it is, so what is the specialty of GAP? Specialty of GAP is that it is useful in studying groups. There are so many programming languages, the traditional ones, usual ones, they have their own data structures, they have their own structures, and not many of them do support groups. So here you can actually define groups, you can play with groups, you can define maps between groups and do calculations which otherwise you would be doing over a piece of paper. So it's useful in studying groups. Representations, I have not mentioned what representations are so far. Probably in coming lectures a bit of representations is what we are going to see, but as a rough way of understanding representations would be that the same group incarnates itself in various forms, in various examples, in various different real life situations. So Rubik's Cube, as I said, it's representing something, it's representing, it's a tangible representation in a sense, it's something that you can touch. It's a representation of its group, Rubik's group, and we are going to talk about Rubik's group as well. But in general, representations concern expressing elements of groups as if they are doing something. They could be matrices, they could be permutations, or maybe some other maps that could be relevant in certain context. So we are going to learn about representations. Rings, probably some of you know. They are objects with 2 operations and there is compatibility between those 2 operations. Vector spaces, most of you would know. So all these algebraic structures can be quite nicely understood via the software called GAP. And as I said, if your machine is Linux, very good. Otherwise on Windows and Mac platforms as well, you will install this software. And the website of GAP, gap-systems.org, is a free software and it's a free in various senses. You can freely distribute it, you can make changes, you can add, you can contribute to it, you can make certain packages and donate it to the GAP systems, and it's all free of cost. So let's see what GAP can do for us. So the command line through which GAP runs quite nicely. So here is GAP. This is how the GAP screen looks like, and you can do various calculations on this. Many calculations are as usual like what you were doing in other programming languages. For example, as basic as this, I am just saying 2 plus 3, 2 plus 3, and it will tell you the answer. And there are other commands as well. For example, let's see, 2 to the power 4, it will tell you the answer, quite easy. Factorial, say 5, and this is something, after every command you have to give the semicolon. Factorial 5, oh yes, it does recognize factorial 5, and then there are many inbuilt commands. Let's see, is even is even to, there is no such command. Let's see, is prime, is that a command? Is prime 5? Oh yeah, there is a command, is prime 6? No, there is no such command. So all the usual things it does, all the usual calculations it does. Let's see if it can factorize something. Factorize, also the command names are quite usual, easy to remember. Factorize, say 10. It doesn't. Maybe factors 10, says 2 and 5. Factors 12, 2, 2, 3. So it does it. And then there is a nice command called collected. So collected factors 12. So it will convert it into bunches. So there are 2 to the power 2 times 3. So 2 to the power 2 times 3. So first is the integer, and 2 is the second is exponent. So integer to the power exponent times another integer to the power exponent. 2 to the power 2 times 3 to the power 1. So like that you can do all the things which usually you could do with the various programming languages. You can run loops also with this. So let's see a few more commands. Let's try to divide. 2 divided by 3, it simply says 2 by 3. So it doesn't try to approximate things, it doesn't try to put things in decimal fraction, because sometimes when computer puts certain expression in the decimal form, there is an error involved. So gap tries to be as accurate as possible. Let's see what kind of programs it can run. So first we are going to see programs which are not quite group theory programs. This sample program, what does it do? It just calculates. This program runs the square root of say in this case square root of 2 or square root of any given number x. The algorithm which is there is quite classic. This is the algorithm which was there in Sumerian civilization, much ahead, much before now, more than 2,000–3,000 years. So what it does is it runs a loop. So for certain loop, supposed to do certain things. So those who are familiar with programming would understand what is happening. This is usual. This is usual in any programming language. So you start with a guessed square root. So x is what for which you are looking for square root. T is something which is guessed square root, some guess initial value, and E is the error. And in each term you improve your guess by this. Now the point is, why should it work? And that's genius of Sumerian people. It should not be very difficult for you to work out that why this way of iterating, this way of assigning new value to your guessed value of the square root is right thing to do. So, and then just write it in the decimal form, float t. So what does float do? Let's go back there and see. Float 2 by 3, let's see what it does. So it does output your given input in the decimal format. It's a sample program. So let's see what's the output of this, and I am iterating it 20 times. So I am just giving the path of the sample program. So this is the way you write your program, and the file that I had shown you was here, sample program.g, and this is the path of the file, and now I am going to execute it. So one way to execute is to read it like this. Read within quotes, you put the file name, the whole path, and see what it does. So I am going to enter. there is an error. What should have been the error? Let's go back to the program and see. X is something. So what is X? It doesn't know. What is T? It doesn't know. So we have to ask whose square root we want, and then what is our guessed value of the square root. So let's go back and correct that error. So now it is in some break loop. I'll come out of it by writing quit. I do that, and now let me define X. So this is a way to define X. Colon is equal to, say I wanted the square root of 10, and let me say the guessed value T is let me say 3, and then I run the program. Then I just call this program using read command and see what is happening. So it has gone into a loop this time. So here I am giving some value of X. Say X is 2, and T, say just some guessed value of the square root, say 1.5, and I am calling the file, the program file, like this, and see what happens. So it actually gets a square root after 20 iterations, 1.4142 or something, and this is the program. So all the usual things that happen in the programming language, they are there, looping is there, and let's see what is there for groups. So how can we make gap understand, gap remember how it should store groups. So here is a nice way I am defining groups. So G is say there are inbuilt groups which it knows. So G is symmetric group, say 4. So this is going to store in the variable called G a symmetric group on 4 letters, that is S4, which has 24 elements. So it has stored something, and then all the interesting things. So order of G, how many elements are there in G, it will tell you how many elements are there. There are 24 elements, and what other things can you do? Let's see. Subgroups of G, there is no such function. I can pick a random element from this random G. So it will pick some random element from this. So it has just picked some random element 1, 3, 2. Once more I do some other element. Once more I do some other element. Interesting thing is that you can loop over the group. So how does it do? So for G in G, do. Now let's ask it to do something. So well, first let me make a list. So L is empty list, and now I can add in this for G in G, do add to this list L the element G, and then I just close the loop. So DO is do and OD is just closing the for loop. So it has put in this list called L all the elements of G, isn't it? It's a quite intuitive command, and then I see what is L. So it lists everything, and I want to see the say fifth or fourth element in the list. Is going to show 2, 4, 3. So 1, 2, 3, 4. That's how it's showing. What's the size of L? It's of course 24. So you can store elements in this. Or if you want to say 5 random elements from this group, you can store. You make a list. I am just emptying the list. So this is empty list, and then I can do for G in G, or rather for I in 0, 4, or say 1, 5, do. So it's making a list. So from the list, so whatever there in the 1, 2, 3, 4, 5th place, it's going to store it. So do add to the list L some random element, say random G OD, and then we can see these are some 5 random elements from this. So it can do all these kind of manipulations, and one can multiply all the elements of the group for, so I will start with say x is equal to this. So this is notation for oh, there's some problem. This is there's something, we'll edit it later. So I just want the product of all the elements. So what do I do? I first restore the identity element. So let me call it x is equal to identity of G, that's identity element of G, and I do for G in G, do x is equal to x into G. So it's multiplying all the elements of the group. So you start with identity, and in identity you keep adding all the elements. Do this, and then I close it. So the variable x in the end is going to store the product. So in this case the product is 2, 3, 4. Okay, so just some fun things these are. There are some inbuilt examples of groups which are stored in this. Apart from alternating, apart from symmetric groups, you have what are called alternating groups. Alternating groups, say, or alternating group on 5 letters, and of course you can check the order of this. Order meaning number of elements in this. So order in this order. So last. So this command is useful. Whatever is the last output, does it like this, or I could have just done it like H is alternating group on 5 letters, and then order of H is this. So you can play with the groups. There are more inbuilt groups. For example, there are certain matrix groups. G is a spatial linear group of 2 by 2 matrices with, say, a spatial linear group, 2 by 2 size, and over field of 3 elements. So it stores it for you. What is the order of the group? It will output it. So all these are interesting things it does. And now we are going to understand how we can use it to solve Rubik's Cube. So first of all, how to tell this software, this gap, what is Rubik's Cube, because there are so many moves, right? There are so many moves here, and everything is essentially a permutation, right? So that's where we are going to use the idea of generators and relations. Relations we won't care much, but at least generators. So you see, when I am having Rubik's Cube here, it's being generated by these kind of moves. Moves in the left, moves in the top, moves in the right, bottom, front, and back. So there are rotations by 90 degree, right? All these are rotations by 90 degree. I am rotating only one layer at a time, top or bottom or front, like that. So let's see, let's go back and see how a Rubik's Cube can be stored in this. So these are some basic features. We have seen how to maintain lists. We have seen that the gap can do looping and we can define certain groups. As you read the gap manual, you will realize that there are other ways, there are so many other groups also, and the same groups also you can store in the group, in the gap in different ways, sometimes in terms of generators and relations as well. So maintaining lists I have told. Sets, just quickly I will say, take a list L and so let us see what L is as of now. L is this, and let me just say X is suppose the first element of L. So L is this first element of the list, and I add to this list the element X again. What happens? So you can see in the end there is 2 4 here, right? The 2 4 is here in the end. So there is a duplication in the list, but set does not have duplication. So I can convert this list. So I can have some S which is set of L, and now it is just one at a time. So set is having one entry exactly once, but list can have multiple times same entry. Multiplicity could be there. So that is list. Sometimes lists are useful, sometimes keeping your data in the form of set is useful, depends on the context. So we have we know how to define groups in gap, we know how to manage lists and sets, and looping also we have seen that we can loop. And now we are going to understand how one can put Rubik's Cube in the gap. So let us see, and after that we will write a program to solve Rubik's Cube. So that is a group theory problem for us. First let us see how Rubik's Cube can be stored inside gap. So when I say Rubik's Cube, what I actually mean is group, the Rubik's group. So that is a Rubik's Cube. What do? I just open this. I just open this in the way that here I have say top, here I have say left, here I have right, so here I have say bottom, and this is back, and this is say front. So I can open my Rubik's Cube in this fashion, right? And everything is about permutations. So let us see what kind of permutations happen. So for that I am going to present solved cube in this fashion. So I am going to name all so this face, all the small portions, all the small squares or tiles on the periphery, on the edge, I am going to name, and this stands for T stands for top. So I am just opening it like this. So the way I had put the nomenclature in the earlier slide is slightly different. Here I am opening it in this way, so that this is front, that is top, that is left, right, back, and bottom, downside. So I have named suppose all the small tiles by 1, 2, 3. So let me just say that this is solved cube, solved Rubik's Cube. So I have named 1, 2, 3, 4, then top, 5, 6, 7, 8 and like that. And now it's interesting what happens when I rotate. So let's concentrate on this. First, let us understand that the group which is relevant here is as 48. So how does number 48 come? You have 9 small squares here and there are 6 faces. So 9 into 6 is 54. But as you see, if I just do this, this one is not moving, the central one. As I move this, the central one is at its place, it is at its own place, so it's not moving at all. So there are 9 into 6 minus 6, only 48 numbers which are being permuted. So 48 of these numbers which I have written, they are being permuted in the process. Let's go for the top thing. So what is happening when I am rotating by 90 degree? That is one single move, and that one single move I am denoting by t. And let's see what is happening when I am doing that. What happens to 1 when I rotate by 90 degree? So 1 comes to this place, right? So that's what I have written. 1 goes to 3 and 3 goes to 8, 3 goes to 8 and then 8 goes to 6, 8 goes to 6 and 6 comes back to 1. So one cycle is complete. This is how we write permutations, as I had told you earlier. So 1, 3, 6, 8, 1, 3, 6, 8 is a permutation. So suppose this is a top one and I am rotating, this is it. But you have to be careful, because when I am doing this, there are 4 other sides. So when I am moving the top one, then except the bottom, everything else is permuted, right? So this face also gets permuted, this face also gets permuted, and this front and back, they also get permuted. So in what fashion do they get permuted? Let's see. What happens to 2? So first let's just fix the top one. So 2 goes to 5, 5 goes to 7, 7 goes to 4, 4 goes to 2. So I have 2, 5, 7, 4. So top we have taken care of. Now what about the left one? So all that is happening, all the things that are happening above this. So when I am moving the top, only the entries which are above this red line, they are being affected. Bottom, nothing happens. So what happens to 9? So 9 moves. Actually, if you name it and if you label it, play like this, you would realize that 9 actually goes to 33. So it goes like back. And then what happens to 33? 33 goes to 25. So 9, you leave 2, 33, leave 2, 25, leave 2, 17, and then back to 9. So this kind of cycle happens. What happens to 10? Similar kind of thing happens to 10. So 10 goes to 34, exactly in the same fashion, some translating fashion. 10 goes to 34 and then 34 goes to leave 2, 26, then leave 2, 18, and 18 is again back to 10. And similarly you have 11. So all the permutations happen only at the top level, but except bottom, every other face affects some permutations. So this is a typical element, and this represents rotating the top face in clockwise direction. So in this clockwise direction, I am moving the face. Now what can I do? I can actually write this kind of move for not just top, but for left, front, right, back and bottom. For all faces, I can write these kind of moves. So these are precisely what are generating Rubik's cube, right? So Rubik's Cube is actually generated by these kind of moves only. That's quite interesting. How do we find out how many such combinations are there? It's extremely difficult because there are so many combinations. There are so many combinations of this. So let's see how we can store all these moves, and then how can we process all that information into something which can solve Rubik's Cube for us. So I hope you could understand how a single move is expressed in this. So next time we are going to write all the moves of Rubik's Cube and we are going to generate a group. Interesting thing would be to see how much is the size of the group, and then we would try to solve the cube if everything goes well. So just wait. In the meantime, if you want, you can write other moves. So other moves corresponding L, F, R, back and bottom. Yeah. So see you next time.